So now we want to start to look at integration. And in order to do that, we're going to do this exercise here in which we try and motivate what the idea behind integration is and how it has to do with antiderivatives. We'll get into the details of that soon, but this is just an exercise to make you think along the way that we're going to need to do when we start talking integration. So let's take a look at this. We want to figure out what to fill in the box here. So instead of being asked to take the derivative of a function, I'm being asked here to think of a function which, if I took the derivative, I would end up with what's over here. So when would I get 2x as a derivative? Okay, well, we saw that a lot. And in fact, we know that if you took the derivative of x squared, you would get 2x. Right? Now, interestingly, it turns out that that's not the only answer that works there. All the answers are going to look similar, but yes, we could have said x squared plus 1, or we could have said x squared minus 5. Those would have worked as well, but let's just think of filling it in with one answer that works right now. All right, so if we go to the next one, the derivative of some function is cosine x. Well, we remember that the derivative of sine x is cosine x. All right, now the derivative of some function equals x squared plus 3. Okay, well, when would we get x squared? Well, we would get x squared from x cubed, but if we took the derivative of x cubed, we would get 3x squared. And the problem is I don't want that 3 there. So I would have had to have something in front of the x cubed that would get rid of that. In other words, imagine if I had 1/3 x cubed. Well, then the 3 would come down, multiply the 1/3 and become 1, and then I would just get x squared. So I actually need a 1/3 in front in preparation for when that exponent comes down in the differentiation. I need something to cancel it out. All right, now when would I get 3? Well, we knew we got a constant as a derivative when we had a constant multiplying x. So that would work. All right. The derivative of something is secant squared x. Well, again, now I have to go back to my memory and say, I saw a trig function whose derivative was secant squared. That was tan x. All right. And then, finally, when would I get the derivative of some function to be x plus 1 over x? Well, x would have to come from x squared, but again, x squared on the derivative is going to put a 2 out in front, so I'd need a 1/2 there in order to cancel out the 2 that's coming down. So that'll give me x, and then when did I get 1 over x as a derivative? That was a special case from ln of x. Okay, so what we were doing there is going to lead in what we're going to talk about. It's doing backwards differentiation. We also call it anti-differentiation, and that's going to lead us to integration, and that's the whole idea. So instead of taking the derivatives of functions, we're going to try and reverse that. We're going to try and say, what function would have been the original function that if I took the derivative of it, I got the thing that I have?